4.2, Function Operations. So in 4.1, we finally introduced the concept of a function. Well, oftentimes whenever we introduce a new quantity in math, we want to see what can we do with it. Remember whenever we introduced complex numbers? We introduced the complex numbers and then we said, how can I do addition, subtraction, multiplication, and division on the complex numbers? We're going to do something similar for functions. Since we've introduced functions, we want to see what kind of operations can we work with on a function. So, starting our first definition for this video. If I have two functions, f and g, we can define the sum or difference, the product, and the quotient of f and g as follows. I have f plus g of x. I define this to be f of x plus g of x. Or I can say f minus g of x is equal to f of x minus g of x. In other words, it looks like I'm just splitting apart my expression. We can see here in the second line, this is f times g of x, which we define to be f of x times g of x. Similarly, f divided by g of x, this is f of x over g of x. This is how we're translating our new notation. So, since we are familiar now with this notation, let's go ahead and look at example 1. Suppose I told you that f of 3 is equal to 2 and g of 3 is equal to negative 1. Remember what does it mean whenever I say f of 3? F of 3 means that I had some function and I plugged in 3, and my result became a 2. Similar thing for g of 3. So if I look at part A, f plus g of 3, I always recommend that students go ahead and translate this over. That is, let me go ahead and split this apart into f of 3 plus g of 3. Well, if I compare these two, f of 3, we have that. F of 3 we know is 2, so this is equal to 2 plus g of 3. We know that g of 3 is negative 1. So I'm just doing what's 2 plus negative 1? I get, well, positive 1. And that would be my final answer. So again, we're translating our new notation into what we're a little bit more familiar with. So for part B, you can imagine I pretty much have a very similar situation. F minus g of 3, that is equal to f of 3 minus g of 3. Using what I know from my instructions, I know f of 3 is 2 minus g of 3 is negative 1. So I have 2 minus negative 1, or in other words, 2 plus 1, giving me 3. So I'm done with part B. So in other words, all I'm doing is I'm applying this operation to my f of 3 and g of 3. So see if you can get the answers for part C and D. F times g of 3, this should give me f of 3 times g of 3. Once again, we know that f of 3 is 2, g of 3 is negative 1. So I have 2 times negative 1, or just negative 2. And then for part D, my last one, f over g of 3, I can read that as f of 3 over g of 3, which should translate into 2 divided by negative 1, or just negative 2. So we just did some function operations, finishing up our example 1. So for example 1, this was actually pretty nice because I told you what f of 3 was and what g of 3 was equal to. But we know that functions aren't always clear-cut like what I have here. What if my functions are just expressions themselves? That is, what if I don't give you f of 3, but instead I give you f of x? That leads us into example 2. Let f of x be x squared minus 1, and g of x be x minus 5. Simplify the following operations. For part A, I have f minus g of x. Just like before, I recommend that we translate this over to something we're more familiar with. We can write this as f of x minus g of x. Well, we might look at this and say, what's going on? But remember, we have our beginning information. I know what f of x is. I know what g of x is. I can rewrite this as x squared minus 1, that's my f of x, minus g of x, what we have here. So now my job is to simplify this and clean it up. So if I want to clean this up, I have x squared minus 1 And then remember, I'm subtracting this entire expression. So I should distribute my negative, giving me minus x minus negative 5, or in other words, plus 5. Now if I combine any like terms, I'm left with x squared minus x plus 4, giving me my final answer. There's nothing else I can do to simplify here. Let's continue down on this route. For part B, I have g over f of x. My first step will always be, let's translate this and split it apart. In this case, I can write this as g of x over f of x. Once again, I know what f and g are. We know that g is x minus 5. We know f of x is x squared minus 1. I'm looking at this and I'm going to say, well, there's not much else we can do here for simplifying. We can't combine any like terms. Maybe I can factor, but nothing's going to cancel out in this example. So I have my final answer already. Now we can move on to our next one, part C, g times f of 3. So once again, let's translate this. We can write this as g of 3 times f of 3, like so. Well, I don't know what f and g of 3 are. I know what f of x and g of x are, but I don't know what g and f of 3 are. So before I move further, I need to figure out what these quantities are. So I'm going to do some work on the side. So on the side, g of 3. Remember, g of 3 means what happens if I take g of x and replace my x with a 3. In this case, instead of x, I have 3 minus 5, or just negative 2. For f of 3, again, I do the same thing. I replace my x with a 3. In this case, I get 3 squared minus 1, which gives me 9 minus 1, or 8. So by plugging 3 into my original functions, I know what g of 3 and f of 3 are, respectively. Well, now I'm going to go ahead and take these two values and plug them into my original expression. We said g of 3 was negative 2. We said f of 3 was positive 8. So now I'm asking what's negative 2 times positive 8? I get negative 16. And thus we're done with example 2. We now know how to deal with some function operations. So for the most part, there's not much variation that we're going to be dealing with here. We have addition, subtraction, multiplication, and division. Well, there's actually one more operation we can talk about whenever we're dealing with a function. The last operation we'll talk about for a function is composition. So our definition, given two functions f and g, the composition, denoted by f of g, notice here I have an open circle. We define it to be as follows. F of g of x, that is what happens whenever we take g of x and we plug it into my function f. What I personally like to do is I like to write this as f bracket g of x. Our brackets and parentheses don't mean much different for us in this case. I like using the brackets to indicate that, again, I'm just taking g of x, whatever it may be, and I'm plugging that into f of x. So we read this as f composed with g, or just f of g. One thing I want you to be careful about is that this open circle is not multiplication. Multiplication does not have an open circle, so make sure you're careful about that. So let's see what happens with composition. Example 3. Suppose I have the function f defined by a set of ordered pairs, and g of x defined by x squared minus 7. I want you to compute the following expressions. For part A, I have g of f of negative 1. Well, I'm going to go ahead and rewrite this as g of f of negative 1. So I'll write it like this. What I generally recommend for a function composition is that we work from the inside to the outside. So in this case, on the very inside, I have f of negative 1. So if I do this work on the side, f of negative 1, this is what is f whenever x is negative 1. If I look at my relation, or function to be exact, when x is negative 1, then my y value must be 1. So that tells me f of negative 1 is positive 1. That means I can go ahead and continue my equation by saying that this is just g of positive 1. So I have g of positive 1. And here I should be using parentheses, but I'm just going to keep with the brackets to indicate that this 1 really came from my f of negative 1. Well, now I have g of 1. G of 1 just means I look at my g of x, and anywhere there's an x, I plug a 1 in, giving me 1 squared minus 7, or just negative 6. So this is how we're going to work our function composition. Now, let's go ahead and look at part B. I have f of g of 3. Once again, I'm going to go ahead and write this in my sort of translated notation. This can be written as f of g of 3, where g of 3 is on the inside. I'm going to follow pretty much a similar thing to what I did before. On the side, I'm going to figure out what's g of 3. Well, g of 3 is looking at g of x and replacing my x with a 3, giving me 9 minus 7, or 2. Hence, I can go ahead and write this as f of positive 2. Again, we found out that g of 3 was 2, so I just replaced g of 3 with 2 in my expression. Well, now I had to see what is the value of f when x is 2. If I look at f when x is 2, I have the point 2, negative 1, giving me my final answer for part B. So I have parts A and B done. For some extra practice, let's go ahead and look at part C. Once again, I'll rewrite this as f of 2. If I work from the inside, f of 2, I'll do this work on the side, f of 2. Remember that f of 2 is looking at my f function and saying, what y value do I get when x is positive 2? Well, when x is positive 2, my y value, or my f value, it in fact is negative 1. So really now I'm asking what's f of negative 1? F of negative 1, I use the same process. I go to my f function. What happens whenever x is negative 1? I get positive 1. Finishing up our example 3. So we just got a sample of function composition when I'm plugging in a number. But just like what we did for the operations, we worked with operations with a number plugged in, and then we went more general with our x's. We're going to do the same thing for composition. In example 4, if I have f of x is x squared minus 1, and g of x is 2x minus 1, I want to ask, what's the g of f of x? So, looking at this here, once again, I will translate this over to be written as g of f of x, written like so. Again, using parentheses and brackets as needed so that I can determine what's on the inside. Notice here that this is f of x rather than f of a number. That means the best I can do here is I can write this as g of f of x. We know that f of x is actually equal to x squared minus 1. So really, what I have here is g of x squared minus 1. So the question is, how do I even figure out what's going on here? Well, I'm going to do some work on the side. Again, I know that g of x is 2x minus 1. That's in my instructions. Remember way back earlier, I used this empty box notation, where I can write g of x as g of my empty blank is equal to 2 times that empty blank minus 1. So, since I want g of x squared minus 1, I'm simply putting x squared minus 1 into that blank. Now if I put x squared minus 1 into my blank, I end up with 2 times x squared minus 1 minus 1. Now my job is to clean this up. I can start off by distributing my 2 to each term, giving me 2x squared minus 2 minus 1, and then combining any like terms. I have 2x squared minus 3. So I have my final function composition. Notice here that I did not end up with a plain number example. This is primarily because here I have g of f of x rather than g of f of a number. Alright, so we're done with part A. For part B, we're going to do a very similar situation. So I can write this as f of g of x, like so. Well, I know what g of x is. We know g of x is 2x minus 1. And I'm going to use pretty much the same argument that I had before. Whenever I write f of x in that blank notation, I have f of my blank is equal to that blank squared minus 1. So whenever I put 2x minus 1 in here, then I know that f of 2x minus 1 is 2x minus 1 squared minus 1. And now I must clean this up. 2x minus 1 squared. Make sure you're careful with this again. Whenever I write squared, it really means I have 2x minus 1 times 2x minus 1. In other words, we need to FOIL and multiply this out. If I multiply this out, I end up with 4x squared minus 2x plus 1, and then minus 1. The minus 1 coming along from where I was before. And now I combine any like terms. I get 4x squared minus 4x, and 1 minus 1, we get 0, giving me a final answer of 4x squared minus 4x. So we're done with part B. Now for part C, now I have a number involved. As per usual, I'm going to go ahead and translate this over to our other notation. That is, I can write this as a g of f of 2. And there's a couple of different ways we might encounter this. So one way I can work with this is, let's figure out what f of 2 is. I would do this work all the way on the right. F of 2, that means I take f of x and I replace the x with a 2, giving me 2 squared minus 1, or just 3. Thus, I can write this as g of 3. Now, I just need g of 3. This means I go to g of x, and I replace x with a 3, giving me 2 times 3 minus 1, or just 5. This is one way I could have done it. The other way that I might have done it is that, remember, from part A, I know what g of f of x was. We know that g of f of x was 2x cubed minus 3. Well, what I could have done was, since these look very similar, one's g of f of x and the other one's g of f of 2, this simply means that I could have plugged 2 into my answer for part A. So if you plug 2 into your answer from part A, you would also end up with a 5. So there's 2 ways that you can encounter this. So we have example 4 done. Now let's look at our last example. So far, I've been giving you functions as an equation or a set of ordered pairs. Let's go back to thinking of our function as a graph. So for example 5, find the value of f times g of 1 and f of g of 2, where this upper line is my f of x and this lower line is my g of x. So let's start off with the first one, f times g of x. So f times g of, I think I said x accidentally earlier, f times g of 1. If I translate this, this should give me f of 1 times g of 1. If I clean this up, we know we need to figure out what f of 1 and g of 1 are. So f of 1, this means I look at my upper curve, in this case this red-ish curve, and I look at what is my y value when x is 1. Well, when x is 1, my y value is actually positive 1. So f of 1 is 1. What about g of 1? Well, I do a similar situation. I go to x is equal to 1, and I see what is g of 1. In this case, I'm going to get 3. So now I'm asking what's 1 times 3? I get 3 for my first answer. For f of g of 2, again, this is not multiplication, but rather composition. I can go ahead and write this as f of g of 2, where g of 2 is on the inside. So, if I work from the inside out, we have to figure out what g of 2 is. G of 2, that means I go, what is my y value when x is 2? Well, when x is 2, my y value for my g curve is 0. So now I'm working with f of 0. And now I do a similar situation for f. Looking at my f function, what is my y value when x is 0? In this case, my y value when x is 0 on my red curve, we get a positive 4, giving me my final answer. So this is actually our last example on function composition. In particular, we have to be very careful in making sure that we follow the correct order of figuring out what value is which. And so that's all for today's this video.